Hello again, I'm Alex from OpenFort. If you've been paying attention on the EVM roadmap lately, you've been probably noticed a clear narrative building for 2026 is up to be a year of the privacy. In this video, I want to focus on a different angle of privacy you can ship basically today using existing Ethereum primitives with zero changes on the Ethereum client side. Specifically, I'm going to break down the Steals addresses standard, how they're working, why they matter, and how to implement them end-to-end as a developer. So let's start. On Ethereum, usually if I pay you normally, everyone can see your address and can link payments to your main account. Steals addresses change just one thing, that the sender doesn't pay directly to your known address, the main account. Instead, the sender derives a fresh one-time address that only you can control. And then external observer see a payment just like to a random address. So in this diagram, we can see that we have Alice and Bob. And for example, if Bob want to receive any assets from Alice, basically we can go in a scanner and see all this public information. Okay, and if Alice sending to Bob any assets, so external viewer basically can see all these details. He can see also the balances of Ethereum or of ERC-20 token, transaction history, and a different transaction that basically can link to your account. Important thing that I would like to add about Steals addresses, that Steals addresses give unlinkability. It means that this payment is not obviously to Bob. They do not magically erasing of traceability, of course. If Bob later sweeps funds to his public main account, you can often correlate the activity. So Steals addresses are best though as private receiving addresses, not a full privacy stack like shielded pools or mixers, for example. Okay, let's do overview of ERC-5564 that defines the layer for the Steals addresses. In the standard exists event called announcement, basically published to the canonical announcer contract, so the recipient knows where is to listen. Concept of the schemes, there is in the standard existing some concepts of the schemes that we will talk later. The most common is scheme ID 1, and basically refers to SEC 256K1 with view tags. Also in the standard is a metadata convention where the first byte it's a view tag to speed up the scanning. And there is another ERC that I would like to do overview is ERC-6538 is a discovery layer. It's basically a registry mapping user identity address to their Steals meta address, basically the public key material for the sender's needs. And supports directory registration, also like register on behalf with EAP 712 and EAP 1271 signature, that basically we can register the metadata on behalf of a user. So let's break down more deeply with a lot of details about these standards. So what the popular scheme people are using is scheme ID 1, relays on the standard SEC 256K1 operations. It includes ECDH to create a shared secret between sender and recipient, hashing the shared secret into scalar, point multiplication, and point addition to tweak the recipient sending public key into one-time Steals public key. And then from this public key, we can derive a Ethereum address by hashing this public key and taking first 20 bytes. So the key idea is sender can compute the steals addresses using only public keys. From Bob, the recipient later derive the corresponding private key using their own secret. So don't worry about all these terminologies. So basically there's I prepare example that show the full life cycle of the standard ERC-5564. In this example, you can see that Bob creates two pair keys. One is a spending key pair, controls funds once received. This you can imagine as a master spending route that basically deriving the one-time private keys. And the second pair is the viewing key pair used to detect announcement belong to Bob. Okay, so why basically we need two key pairs? So because Bob can optionally share the viewing key to an external scanning service that basically will help to detect payment without holding overspending power. So Bob publish a still metadata address, typically contain the spending public key and the viewing key, only the public key basically. So in the standard, the format you can see in this example, it's look like that basically we concatenating the spending public key with the viewing public key, and this is we can call like a payment link that we are transferring directly to Alice, or we can basically register in the contract this information, and basically Alice can parse our payment link that we shared. In a practice, the most usable flow is that Bob register his steals meta address in the contract ERC-6538 registry, and then Alice doesn't need Bob to DM a long string or use external services to transfer this meta address. And then Alice can just use Bob's normally identity address, or for example in ENS it's possible to register metadata, and this is resolve it and fetch the metadata from the registry contract. So there is like canonical address of the ERC-6538, so then Bob basically need to call to the function registry key that getting as a parameter the scheme ID. So as you know, usually people using with the scheme ID 1, and we are publishing the stealth metadata address bytes that I show you in this example. The string basically 66 bytes we are publishing in the contract of the registry key. Okay, so let's move for the next step. And after Alice resolves Bob's steals metadata, if it's from the contract of the standard ERC-6538 or direct share, then Alice generates an ephemeral key pair for this payment. Then Alice computes the steals address using ECDH plus hashing plus point addition. Then Alice sending amount of Ethereum to steals address, just normal ETH transfer. Then Alice post an announcement to the standard ERC-5564 announcer contract, so Bob can discover it, that basically Alice sent payments to steals address. Then Bob scanning announcement events, detecting the payments using his viewing key in this case, and derives the steals private key by spending private key. So refer this diagram, you can see exactly the example that I shared right now. So generate ephemeral private key, then compute shared secret, and we are hashing this secret. And the first byte, it's basically going to be a view tag. Then we are computing a tweak point. Then we are computing the stills public address. So you can see we are in this flow, we are using with the viewing public key and spending public key of Bob that basically Bob share with Alice, and then we are hashing the public key and taking the 21st byte, and this is how we are creating stills address. So basically Alice can compute only the address, not the private key. This is very important, and after that Alice can send assets to this address. The major key point here is on chain that there is no recipient equal to Bob. So the stills address that Alice created right now, it's a fresh address. There is no link to Bob. So basically you can think as an external viewer, there is just created a new fresh address that asking for payments, or it could be in the same way that Alice just derive a new address and send their assets. So it would not break privacy. And of course, the ERC-5564 standardized an event stream. So the sender calls the announcer contract, which emits event. The event include scheme ID, stills address, caller, ephemeral public key, and metadata. So the canonical announcer exists in different chains, and of course we can deploy to other EVM support chains that basically with the same others. Then of course the important thing that the first byte of the metadata must be the view tag. That's how basically the recipient can quickly discard most announcement during the scanning. What include exactly the event? Let's a little bit breakdown. So we have in the event basically the scheme ID that we know the popular one is the scheme ID 1. Then the stills address. That basically we got the assets here. Then we need to publish also the public ephemeral key that Alice created just to generate the stills address. Then we are transferring announcement metadata. This is going to be like the view tag that basically we are getting from the hash of the secret. And of course, if, for example, we transfer Ethereum, so we are transferring 4 bytes, basically that announce that there was transfer of the Ethereum, the address of the Ethereum, and the amount that we are transferring. In the case of ERC-20, here is going to be the hash selector of the function that we use if it's transfer. So here going to be the 4 bytes of the hash selector and the address of the ERC-20 token and the amount. So inside the contract, Alice announced this, and there is emit event. Also, the event will include the caller address. After Alice emitted the announcement event with all information, so basically Bob needs to monitor the announcer logs events. Bob doesn't know in advance when Alice will pay, so he needs to scan incrementally for the last proceeded block. So for each announcement, he reads the public ephemeral key and the view tag. Then he, based on that, compute the secret hash and taking the first 1 byte and comparing with the view tag, basically that he scanned from the log. So you can see here the full flow that Bob using to identify if this announcement was for him. So that 1 byte filter basically rejects approximately 255 out of 256 announcements before doing the more expensive work. When it match, so Bob recomputing the public stills address and verify it match announcement steals address the recording as mine. So basically you can see in the diagram, after the Bob identified this announcement was for him, he recreating the private key of the steals address, checking the address, deriving from this private key the address, and comparing what basically Alice announced. And this is how he understand that he took over control of the steals account that created by Alice. I would like to wrap up the full life cycle of the steals addresses, so we can start from the beginning and quickly make overview. So Bob basically needs to create random pair keys. One is spending key pair, and the one is view key pair. It's basically not related to his main account. These keys he can store in external service, or he can store locally, or create in some trusted environment. Then he needs to concatenating the spending public key and viewing public key. Then he needs somehow to register or send to Alice that she will understand which basically the steals meta address to use. Then after she got this information, Alice creating ephemeral private key and the public key. So basically she using with the ephemeral key pair to compute the steals address. So also the Alice in this case not using in any moment with her main account. After that she using with the meta address that Bob share. She computing secret, then she hashing the secret. She taking the first byte of the hash. It's basically gonna be a view tag. Then we are creating the public steals address. So basically then we are doing a hash function on the public key and taking first 22 bytes just to create the address. And then Alice can transfer any asset to this address, if it's Ethereum or any ERC-20 token. In this case, Alice can send assets from her main account, or also to use any private service to top up this address. But for the external viewer, basically in on-chain, it's going to be like just a fresh account created and then Alice top up. So it could be that Alice basically just created an address and she transfers some amount of her asset to this account. And then she needs to create the parameters for the standard ERC-5564 to execute the function announce. So as we can see, there is like some parameters. One of them is the scheme ID. It should be 1 because all this example it's based on this scheme ID. It relays on the SEC 256K1. Then also publishing the others of the steals address. Basically Alice computes based on the steals meta address of Bob. Then she publishing the ephemeral public key and the metadata that we break down before, executing the transaction, and inside the contract emitting event with all necessary information that Bob basically need to parse. In the same time, on the Bob side, after he sharing the steals meta address with Alice directly or registering this in the contract ERC-6538, Bob start monitoring the events of the contract ERC-5564 and checked every event if basically the announcement belongs to him. So here taking his private viewing key that he generating before, and from the event log he parsing the public ephemeral key Based on that, he's creating secret. He hashed the secret, taking the first byte of the secret and comparing with the view tag that was announced. If it's correct, so basically he understands the announcement was for him, then by that he recovering the private key of the steals account that basically was generating by Alice, the address. Here is the private key. So this is how he basically can take control over the steals address that generated by Alice. So here it's the main point. I think that I would like to point you that this address, it's not linked with Bob in any way, because Alice sent their assets, and if Bob not connecting or linking somehow with his main account, like for example withdrawing the assets and transferring to his account that basically, I don't know, main account or link with the ENS service. So then of course Bob discovering that this steals address belongs to him. But in a case, for example, if Bob receiving payments from different sources and every time he creating steals address, and every time, like for example, let's say he got 10 payments, if he want to spend, so of course he have this private key and he can spend these tokens and or use with different services, just not to link between his main account and the other steals addresses, because for the external viewer on chain, he just see a random address basically that's spending an amount of tokens or transferring to another source. So you can unite between steals addresses, but basically the point here is not to unite, just spend the amount that you need that sits in the steals account. So here is the overview of the steals addresses and how we can use basically. There was a lot of technical stuff. Also, I want to show you some POC that I done with front end, and you basically can imagine this use case for the steals addresses. In this example of the POC that I've done, I just want to show a use case, for example, for on-chain private payments. So just imagine you, like, for example, you can be a freelancer or just receiving any payments from any source, like your salary. So everybody can on-chain see the receiver. So if you are receiving to your main account, so the external viewer can spot all your history transaction balances, the ERC-20 balances, and link everything to your main account. Basically all activity, the external viewer will understand that it's your account basically doing any type of transaction. So here in this case we can use with the steals addresses standard and to receive payments to a fresh derived address that can't be linked basically to your main account, and nobody like externally can spot all details about your main account. So here, for example, we want to receive USDC. We see that we have main account, there is some balance, still didn't got any transaction. Also main point that I'm working with Anvil local network, but of course in the backend it's doing the full cycle of the standard that we was talking here based on this example. Then, for example, we want to receive a certain amount from OpenFort as a payments for our service. So as you can see, we are creating here the meta address that we need to share with the payer. For instance, we want to receive 500 USDC, and of course it's in the backside creating the steals address and sending to this address privately the 500 USDC. So now if we will see the accounts, so here we have private accounts that include 500 USDC managed by the owner of this account. So we have, you can see main account, and there is another account, that fresh account, that we also can take over control by recovering the private key from the announced data that basically the payer shared. For example, we want to receive again. So every time that we want to receive again, they will generate a new private account, stills address, to receive any payment to the fresh stills address. So for example, let's say 300, then again receive. Then you can see basically we are creating another private account that got this payment. So every time we don't need, also the important thing, we don't need to store these private keys anywhere. We can just store the details that we need from the announcer. We can store basically the public ephemeral, and we need to store the metadata, but also we don't need to store, because if we want to recover the stills private key, we don't need to store. We just need the details basically of the public ephemeral and the stills others, just to understand that basically these others belong to us. So in this way also we don't need to store private keys anywhere. So every time that we would like to spend any USDC from these accounts, we can do system that recover these private keys and then take over control and spending any amount of the USDC. Alright, so we got to the end of this video guide about stills addresses standard. So the last thing that I think important you should remember from this video, that this standard basically providing unlinkability. What does it mean unlinkability? It's that you can't link between Bob to the stills address. So basically, if Alice sending any assets to these address, you never can know that recipient, this is Bob. And Bob always can take control of this address and spend the amount, the balance basically that exists in this account. But it's not solving traceability, because everything is on chain. Everybody can see that Alice, if it's from her main account or from any other account, that basically assets move from address A to address B. But nobody can trace that this address belongs to Bob. So this is the main point I think you should remember all the time. So here was Alex from OpenFort. Happy to share this knowledge with you, and see you in the next video. Bye bye.